good afternoon, all of you. Is it visible?
Yes, sir.
Okay. So last day I have started the memory interfacing technique. I've discussed some of the topic of from this portion. So today I will continue it. And last day one example has been discussed, which is based on the logic gate. Hmm. So interfacing diagram interface one microprocessor IC with an EPROM IC using NAND gate circuit. Okay, we have already done it. So another technique is to be discussed over here using the same type of design interfacing diagram, which will be connected through the decoder IC. Okay, so when a number of memory chips having similar capacity have to be interfaced with the 8085. At that time, decoder IC such as 74 LS138 uh, with active low outputs are useful. Okay, so you have to remember this output. This is an decoder. This is a decoder IC. It's one kind of 3:8 decoder. I hope all. I think all of you are familiar with the decoder circuit. 3 is to 8, 2 is to 4, 3 is to 8, 4 is to 16, like this. So this is 3 is to 8 decoder IC where 3 in, so all here the output lines are active low. Okay, uh, in this context with the microprocessor you have to connect one such decoder IC whose output must be low. So a single 74 LS138 IC that can be used to interface up to 8 memory chips because it has 8 output lines. So you can connect 8 memory device, either RAM or ROM, with these outputs. Okay, so okay, first I will just review some of this uh, feature of this IC decoder IC. So it has 3 select lines, as you can see over here, A, B, and C. A is the least significant bit; it is used as least significant bit. C, it is used as most significant bit. Okay, C is the MSB, and 3 enable inputs. Uh, Among these 3 inputs, G1, G2, A bar, G2, B bar, among these 3 inputs, 2 active low enable signals are used, which are G2 A bar and G2 B bar. Only when G1 that is equal to 1 and G2 A bar and G2 B bar is equal to 0, only at that time the IC functions as a decoder. Okay, under this condition, depending on the value of the select inputs, one of the output will be low, that is logic 0. If G1, but if G1 is 0 and G2 A bar and G2 B bar is 1, all outputs are 1, independent of the value of the select inputs. Okay, so here, okay, another 2 pins are available, that is the supply voltage pin and the ground pin. It must be connected in such way that always the logic will be maintained, um, properly maintained, okay, to operate this decoder IC. Now this is the table where you can see the how many inputs are available for this 3 to 8 decoder IC and how outputs can be affected uh, according to the condition. Okay, like as I have told you earlier that the G1 and G1 and G2, there are 2 pins. One uh, like here G1 basically it is the 1, and G2 is G2 A bar and G2 B bar. Okay, so when G1 is 1 and G2 is 0, at that time the select lines are 0 0 0, so only Y0 will be selected. You can see it from the previous figure, that is when G1 is 1, it is active high signal, but these are two active low signals. When this one is 1, these are 0 0. At that time, if the inputs are 0 0 0, then only Y0 will be selected. If this one is 0 0 1, at that time Y1 will be selected. Okay, sorry, 0 0 1, at that time Y1 will be selected, and when it is 0 1 0, Y2 will be selected. When it is 0 1 1, Y3 will be selected. When it is 1 0 0, Y4 will be selected. Then 1 0 1 for Y5, 1 1 0 for Y6, and 1 1 1, then Y7 will be selected. Okay, so that is the function of this decoder IC. So now I will explain one such example which is used based on this decoder IC to connect the to interface the uh, microprocessor IC with this EPROM chip. Okay, so move on to the next slide. Okay, clear up to this much? Do you have any queries, any doubt? Okay, so now coming to the second example where interface 2 numbers of 2764 EPROM ICs, which is 8K cross 8 in size, with the 8085 such that the starting address assigned to the chips are 0000 and 8000H respectively. So I have told you last day that there are two methods to implement this memory interfacing with the microprocessor IC. One is using the logic gate, another is the decoder IC. Now, if you want to connect any single RAM or EPROM chips with 8085, you can use the logic gates. But if more than one device you need to connect with one such microprocessor IC, so here you need to connect two numbers of EPROM IC. So in that case, if there are more number of one IC memory ICs available, then it is better to consider the decoder IC to implement or to design such type of interfacing diagram. Okay, so here 8K cross 8, it has 13 address lines. How can you calculate this one? 8K represents 2 to the power 13. So 13 address lines are there. 2 to the power 13 equals to 8K. Okay, why 2 to the power 13 equals to 8K? Because we know that 2 to the power 10 equals to 1 KB. 1 KB. 2 to the power 10 equals to 1 KB. Now 8K, which is equivalent to the power 13, and 13 is the number of address lines. So A0 to A12, total 13 address lines will be connected to the both of these this EPROM ICs as well as with the microprocessor IC. Okay, the ending address of the chip is obtained using the um, by adding one FFFF. How? Last day I have told you about the process. Now it is given as the starting address, which is 0000 for suppose EPROM 1 IC, and 8000 for EPROM 2. Now consider the first one, EPROM 1. So write down the starting address in binary form. So it is considered from A0 to A15, all 16 address lines which are there in microprocessor 8085. Consider all of them. Then write down this starting address which is given in your problem statement. It must be converted into binary form. So 0000 means total 16 zeros will be available, and it will be uh, given here in this way. Next, make a partition between the 13 address lines. Those are connected to both of this system, A0 to A12, and the remaining address lines, those are left open. These are used by the microprocessor itself. Okay, so it will be remain same. These three address lines, those are not connected to any EPROM IC. Only these are valid for microprocessor 8085. These will be same from the initial position to the last one. Only the variation will be here, where the A0 to A12 total 13 address lines are available. So make it available from all zeros to all ones. Okay, and in this way you can find out the last or ending address of a particular IC, okay, memory IC, EPROM IC. So make it this 0001, this is 1, then 1111, this is F, then 1111, this is another F, then 1111, this is another F. So the last address of EPROM 1 will be 1 FFF if the ending if the starting address is given as 0000. So what is the size of this address range? It is 8 kilobyte size. Okay, so 8192 memory locations are available, but you don't need to consider in between the starting and the ending address. Only the starting address and ending address is required to connect it. Okay, clear? Any doubt, any confusion? If you have, you can ask me now. If you have any confusion, any queries, is it clear?
Yes, sir.
Okay. So coming to the EPROM IC2, whose starting address is given as 8000. So convert it into binary form and write it down in this way: 1000, which represents 8, then 0000, again 0, 00000, 00000. So 8000 is written in this way in binary form. So make a partition between the 13 address lines and the remaining address lines. These three address lines, remaining three address lines will be same for each memory location from the initial condition to the last one. Only the 13 address lines, those are connected to the both of these system. Only these can be varied from one all zeros to all ones. Okay, so how can you get the ending address? Again, take four binary numbers to present one hexadecimal digit: 1001, which is 9, then again 1111, which is F, then again 1111 F, then last 1111 F. So 9FFF is the last ending address of that particular EPROM IC2. Okay, so memory mapping technique has been done. Now, what is your aim? You have to convert this table into a diagram form. Okay, and for that purpose, you need to use this type of diagram where you have to draw this 8085 on the left hand side, extreme left, and on the right hand side, you need to take two ICs. One is EPROM 1, EPROM 2. Okay, so all of these have 8 bit data address, sorry, data lines, and address bus is over here, which is 13 address lines are required to connect all of these components. Then remaining address lines are only for 8085, which is over here 13, 14, 15. So three remaining address lines are there, so that's why we need to connect a 3:8 decoder IC. Okay, 3:8 decoder IC. So these three lines are used as your select inputs. Okay, whatever be your combination, according to that select lines combination, the required number of output will be activated. Okay, now before going to connect this one, you have to connect these enable input lines, because without these enable input lines, this IC is not working, okay, properly, correctly. So make it properly functionable. Then you have to first connect these enable inputs lines, give them the required number of power supply and the common signal. So G1, which is high level signal, so active high signal must be converted, must be connected to that, to such input where always the 5 volt or logic 1 is available. Okay, so it needs logic 1 every time, that's why it is to be connected with 5 volt power supply. Now ground is available as your logic 0, so these are G2 A bar, G2 B bar, these are two active low enable signal, that's why these are connected to the ground pin. Okay, now when these three signals are uh, suppose 000 or 00, whatever be your condition. So what was your condition, check it out. One time these three lines will be 000 for EPROM 1, and for EPROM 2 these three lines will be 100. Is it clear? This is A13 line, A14, A15. So A13 line needs to be connected with decoder IC input A, then A14 line will be connected to the decoder IC input B, and A15 line must be connected to the decoder IC line C. So what will be the combination? One combination is 000 for EPROM 1, another is 100 for EPROM 2. So in that way it is to be connected 000. So when it is 000, which one will be affected? EPROM 1. So Y0, when these are 000, only Y0 will be activated. So connect this Y0 to the chip enable pin of that IC. Okay, so one IC is connected, interfaced with this microprocessor. So you have another IC. How can you connect it? So for this connection you have to change the combinations. And what are the combinations? It must be 100 according to the memory mapping table, 100. So if these are 100, Y4 will be connected. 100 means Y4. So now the Y4 output must be connected to the chip enable pin of this particular IC. Okay, so now both are connected to this microprocessor as per the requirement, as per the combinations of the select lines, it will be affected, it will be enabled. Okay, operated. And at last when these are already activated, then this is the ROM chip, that means only read operation can be performed, and that's why the output line, output enable line must be connected to the memory read signal, which is available here. Assume that here in this here in this portion already the memory read signal is generated, which is to be connected with the OE bar pin of each EPROM IC. Okay, so is it clear? Any question?
No, sir.
Everything is clear? If you have any question, you can ask me now. Okay, so now coming to the RAM IC. Okay, so until now ROM ICs are connected. So you have another memory device which is called RAM IC. Okay, where read and write both operation can be performed. So each RAM chip, it has a set of address lines, data lines, and control lines. Now address lines are required to connect the memory address, which is coming from the microprocessor address bus, and data lines are connected to the data bus of the microprocessor, and control lines are required to give the control signal like either read or write operation, which will be performed according to the requirement, that must be connected. Now the number of uh, address lines depends on the storage capacity of the RAM chip, as you can see it on for ROM also. Okay, what is that? For example, and 8K cross 8 RAM chip, it has 13 address lines. It has 13 address lines. How? Because the first 8K, it is all the memory devices can be represented in this way: 8K cross 8, or 2K cross 4, or 2K cross 8, or 16K cross 8. In this type of representation is to be used to represent the capacity of each IC, memory IC. Now the first letter, which is 8K over here, it is used to identify the size of that particular memory device. Okay, what is the size? It is 8 kilobyte, 8 KB size. That means 8192 memory locations are available. Second 8 represents that uh, in each memory location only 8 bit of data can be stored. Maximum 8 bit of data can be stored. Okay, in each. So how many memory locations are there? 8000 memory locations are available. In each memory location only 8 bit can be stored at a time. Okay, so that's why when you have to find out how many address lines are required to cover this 8 kilobytes of memory space, it must be 2 to the power 13. And 2 to the power 13 means from A0 to A12. Okay, from A0 to A12, and it has 8-bit data lines. So 8 data lines are available from D0 to D7, and it also has a read. It also has read control signal, which is over here. The OE bar, that is output enable for reading the data. And also it has the write operation pin, which is called the WE bar, write enable bar, and two chip select signal. Okay, two chip select signals. One is CE1 bar, another is CE2. So one enable pin is low, another enable pin is high, and that is the difference between ROM IC and RAM IC. In case of ROM IC, only one chip enable pin was available. Okay, only one enable chip enable pin is was available. Okay, that is this one, C1. Okay, but in case of RAM IC, there are two chip enable pins are available. Among between these two, only one is active low, another one is active high. Okay, so you have to use in that way. You have to give the logic, you have to give the signal in that way, that one signal level maintains the logic 0, another will be logic 1. Okay, so it's a 6264 RAM IC, one example of 8K cross 8 RAM. Okay, now coming to the example, interface a 6264 RAM IC, which is 8K cross 8 in size with the 8085, says that the starting address assigned to the chip is 4000. 4000. Okay, now do you have pen and paper with you, everyone? Okay, so write it down, and you, all of you must share your screen so that I can check the memory map table. Okay, make the memory map table on your copy. If the starting address is given as 4000, then what will be the ending address? How can you calculate the ending address? Perform it on any copy and then share your screen. First write down this problem. Interface a 6264 RAM IC 8K cross 8 with the 8085, such that the starting address assigned to the chip is 4000. So I need to stop my screen sharing, and so I will give you 5 minutes time to make the table, memory mapping table. If you have any confusion, NAND gate circuit. Okay, if it is if you need to connect any one memory device with the 8085, you need logic gate circuits. And if you want to connect interface more than one memory device with 8085, then you need to connect the decoder IC. Okay, it is the better design concept. That's why the NAND gate circuit is used over here. So only 13 address lines must be connected to both of them. Data bus lines must be connected to both of them, 8 data bus lines, and remaining 3 address lines are there, A13, A14, A15. And as per the memory mapping table, A13 is 0, A14 is 1, that's why it is directly connected to the input of this NAND gate, and A15 is 0. So A13 and A15, these are 0. Now to make it high, you need to connect to one inverter over here, so that the input of this NAND gate will be all 1. Okay, all inputs are high, so that the output from the NAND gate must be low. It will generate the low output. So when this NAND gate, so according to the NAND gate truth table, the output of this NAND gate will be low if all the inputs are high. So if you have any inputs as low initially, so you have to make it high. And how can you make it high from low? If you connect an inverter. Okay, so that's why your, according to the memory mapping table, uh, the A13 line is 0, A14 is 1, A15 it is 0. So both of 0 lines must be converted into high using this inverter, and A14 is already 1, that is high state, so that's why it is directly fed into this NAND gate input. Okay, so the output from this NAND gate will be directly connected to the chip enable pin of that IC. It is a low level signal, so this low level signal must be connected to this low level signal. And another chip enable pin which is available for this RAM IC is CE2, which is active high signal, which require active high signal. So that is to be connected with the 5-volt power supply, where logic 1 is available for every time. Now there are two control signals need to connect with the microprocessor. Two control signals are generated from the memory read and the memory write. With the help of these three signals, IO slash end bar, read bar, and write bar, and assume these three signals are already fed into such a circuit that the circuit output must be connected to that uh, control output control pin of this RAM IC. Okay, so memory read must be connected with the output enable pin, and memory write must be connected to the write enable pin of this RAM IC. So that is the interfacing diagram for this particular statement. Okay, what was the statement? Interface 6264 RAM IC, which is 8K cross 8 in size with the 8085, such that the starting address assigned to the chip is 4000. Now coming to this one. Second one, interface 26116 2K cross 8 RAM IC with the 8085 using 74LS138 decoder, such that the starting addresses assigned to them are 8000 and 9008 respectively. So for RAM 1, the starting address is given as 8000. You have to find out the ending address. What will be the ending address? You need to find out using the memory mapping technique. And for RAM 2, the starting address is given as 9000. You have to calculate the ending address. Okay, starting address is given as 9000. Ending address, what will be the ending address? You have to find out using the memory mapping technique. Okay, so as per the size of this RAM IC, it is a 2K 2 kilobyte RAM. So 2K means to the power 11, to the power 11. So 11 address lines will be connected to both of them, all of them, A0 to A10. Okay, remaining address lines must be connected to the decoder IC, so that according to the status of each address lines, the required number of output will be enabled, and that output should be connected to the two RAM ICs chip enable pin, low level chip enable pin. Okay, so this will be over here. So 8000 was the starting address for RAM 1. So 8000 is written in this way: 1000 means 8, then 0000 means 0, then 0000 means 0, then 0000 means 0. This is 8000, which is converted to binary form in this way. So what will be the ending address? So make a separation line. That means only 11 address lines must be connected. So this dash lines, this dot lines have to be used to separate them. So all these lines means from A0 to A10, only these address lines are connected to all of them. That's why these are varied from all zeros to all ones. Okay, write down 1 over here. Then remaining address lines will be same from the initial position to the last one. That's why it is written as 10000 as it was in initial condition. Okay, so now calculate the ending address taking the 4 binary digits for 1 hexadecimal digits. That means 1000 means 8, 0111 means 7, then 1111 means F, then 1111 means F. So that is the memory address range for RAM 1 chip. Then for second RAM chip, the starting address was given as 9000. So write it down in binary form: 1001 means 9, 0000 means 000, in this way. This separation line has been already made. So take this from all zeros to all ones. This can be varied from all zeros to all ones. Remaining will be same as it was in the initial condition for RAM 2. That is 10010. It will be remain same 10010. So now take this value 4 digits into 1. That is 1001 represents 9, 0111 means 7, then 1111 means F, then 1111 means F. That is the last or ending address of the RAM 2. So this is the memory mapping technique for RAM 1 and RAM 2. Okay. Now these 5 address lines or 5 pins are remaining. Okay, so if you can if you have the 3 to 8 decoder, so how many inputs can be connected over there? Only 3 inputs, 3 select lines. So you can take any 3 inputs among these 5, either this one, or this one, or A11, A14, A15. Okay, anyone. But here you need to remember one thing: you must choose such address lines where the variation comes. Means one combination is used to enable the RAM 1 IC, another combination will be available for RAM 2 IC. Now if you have taken 11, 12 and 13, that means all these are 000 for RAM 1, and it will be changed for RAM 2 as 010. Okay, so there are two variations for two status of RAM 1 and RAM 2. But if you have taken this one, suppose 11, 12 and 14, 11, 12 and 14, so instead of 13 you have used 14. In that case, 000 for RAM 1 and 010 for RAM 2. This is also right, you can take it. Okay, but okay, another is you can neglect this one A11 line and connect this 12, 13, 14. In that case, 000 for RAM 1 and 001 for RAM 2. Okay, but you can't select this one A13, A14, A15, because every time this will be remain same. So there is no variation from RAM 1 to RAM 2. For RAM 1 it was 100, and for RAM 2 it was 100. So if there is no variation, you can't select such lines. Okay, you need to keep that variation to to make the different output. Okay, so convert this diagram, so table, into a diagram format where the left hand side 18085 is there, and on the right hand side two RAM ICs are available. uh, eight data lines are connected to all of them, and 11 address lines are connected to all of them. This memory read and write signal is connected to the output enable pin and write enable pin bar of these two RAM ICs. Then coming to the 11, 12, and 13, these three lines. Now take these three lines as 0, 0, 0. If these three lines are 0, 0, 0, which output will be affected? Y0. So Y0 must be connected to the RAM1 IC, chip enable pin of that RAM1 IC. Now second variation is, what is that? It was 0, 1, 0. Now if it was 0, 1, 0, then which output should be affected? Y2. So Y2 must be connected to the chip enable pin of that RAM2 IC. Okay, because all these outputs are active low. Okay, so this is also active low. So you need such active low signal to enable these RAM ICs. And another active high chip enable pin is to be connected with the 5-volt power supply, where logic 1 is available for every time. Okay, now this one, so 11, 12, and 13 is already connected to the select inputs of this decoder IC, 3 to 8 decoder IC. Now what about the remaining two address lines, that is 14 and 15? Now 14 and 15 status was, every time it was, 14 is always 0 for RAM1 and RAM2, and A15 is always 1 for RAM1 and RAM2. So if you connect A15 line with the 5-volt power supply, it will remain 1, logic 1. And if A14 line is to be grounded, then it remains always logic 0. So make it in that way that A14 line should be connected to the G2A bar, G2B bar, and it is to be connected with the ground pin. And A15 line, and you don't need to connect ground pin also, because always A14 line is available as 0. It is not changed anytime. So that's why directly connected. Okay, A15 line is always 1. It is coming always high signal. So it is to be connected with the G1 high enable input of this 3 to 8 decoder IC. Okay, and here VCC is to be connected to 5-volt, and ground pin is to be connected to as common pin. So this is the diagram for interfacing 26116 RAM ICs with the 8085 through 3 to 8 decoder IC. Is it clear? Do you have any confusion? Do you have any confusion? Any doubt?
Sir, could you please explain that A14 and A15 again?
Yes. A14 is, A14 line is always 0. A15 line is always 1. So it is active low always, it is active high. Now according to the decoders, 3 to 8, sorry, 3 to 8 decoder circuit structure, this is high enable pin which requires always logic 1. So A15 line is always logic 1, so that's why it is connected to this pin. And A14 line is always 0 as per the memory mapping table, and G2A bar and G2B bar, it requires logic 0 to activate this IC. So it is to be connected with A14 line. Is it clear?
Yes, sir.
Sorry, I can't hear properly.
Yes, sir, clear.
না আরেকজন কিছু বলছিল মনে হলো. Yes, your voice is clear. অন্য আর কেউ, anyone else? Okay. Okay, so move on to the next slide, where the absolute address decoding and partial address decoding. Now, absolute address decoding is where all of the address lines from A0 to A15 lines are used to interface the memory IC. Okay, but in partial decoding technique, only few address lines are available for memory connection, for interfacing connection. Other remains in don't care logic, either 1 or maybe 0. So this type of condition is called the partial address decoding technique. Now, absolute address decoding technique, it is used for large number of large system purpose, and partial decoding technique is available for small system purpose. Okay. Okay, so these are related to memory interfacing. Now